An object the size of a football field left our sun and sped up. Astronomers saw a real, measurable push that gravity alone could not explain. The immediate takeaway is simple. Something faint and tiny got an extra shove right after swing-by. This visitor has a name. It is Oumuamua, the first confirmed interstellar object ever seen passing through our system. Non-gravitational acceleration means motion not caused by gravity, but by some other force. That force could be outgassing, or sunlight pressure, or something we missed. The speed bump was small, but it stacked up over days. More puzzling, there was no obvious gas tail and no dust halo, so the picture is strange yet grounded. The numbers come from precise tracking, not a hunch. You will hear wild ideas, but we can anchor on data. We know the path, the timing, and the size range. We do not need hype to make this weird, it already is. Bottom line, an alien rock came in fast, turned the corner, then left faster than models said it should. Night on Haleakala, the Pan-STARRS telescope scans a starry grid. A streak shifts against the background, between frames like a tiny intruder. Oumuamua is the first confirmed interstellar object, meaning it came from beyond the sun's family. That matters because it lets us sample another star's leftovers without a spacecraft. Survey telescopes collect repeated images, then software flags points that jump. Astronomers link detections across nights, fit an orbit, and test consistency. If the curve is hyperbolic, the object is not bound to the sun. This one was dramatically hyperbolic, with an eccentricity near 1.2. Its incoming speed at infinity was about 26 kilometers per second. The color looked slightly reddish, like weathered organic dust. Brightness fluctuations suggested an elongated, tumbling body, not a sphere. At peak, it was too faint to resolve, just a changing glint. Models turned those glints into a size near 1 to 200 meters. The surface was likely dark, reflecting maybe 10% of sunlight. That kept it stealthy until it was already leaving. So the picture is simple. We caught a fast outsider by its flicker and math. Picture a pebble passing a bonfire, feeling heat on one side. Oumuamua's path showed an extra outward push after it rounded the sun. Non-gravitational acceleration here means a steady, radial nudge away from the sun. It matters because any extra force reveals the object's makeup and physics. Analysts subtracted all known pulls, then mapped the residuals over time. The remaining signal looked smooth, like sunlight intensity falling with distance. Outgassing can do that because jets fire more when warmer. Sunlight pressure can also do that, since brightness drops with the square of distance. The measured boost was only a few millionths of a meter per second squared. Over weeks, that small push adds several meters per second of speed. Over months, it shifts the trajectory by thousands of kilometers. Example in real terms, imagine a car gaining 1 meter per second per week. You would not feel it in the seat, but the map would drift. Net result, a gentle, sun-centered push was real, and it mattered. A normal comet cooks near the sun and throws off a glowing coma. A coma is the fuzzy gas cloud that surrounds a venting comet's nucleus. That absence matters, because jets without gas or dust would be unusual. Deep images showed no dust fan, even at very low brightness. Infrared eyes searched for carbon monoxide and carbon dioxide, the classic drivers. The limits were tight, far below many small comets at similar distances. If jets were present, they were either extremely clean or extremely weak. Thermal models asked if ice could hide under a crust, then leak sideways. Some venting could escape detection if the grains were big and few. But the required thrust pushed the allowed gas budget to the edge. Spitzer watched and found nothing, strengthening the non-detection case. The evidence leaned away from a normal, dusty comet behavior. So the picture is stark. The shove looked comet-like, but the coma was missing. Now picture a shard of exotic ice, hardly leaving a fingerprint in light. The idea here is simple. Invisible ices like molecular hydrogen or nitrogen could sublimate quietly. It matters because such ices could push without lighting up a plume. Heating from sunlight can free molecules that rush off and give thrust. Hydrogen would be invisible in most bands, and nitrogen is hard to catch. The trick is survival. Can a fragile block endure the long, cold trip between stars? Cosmic rays erode surfaces, and heat leaks away stored gases over time. Models suggest pure hydrogen lumps would evaporate quickly in interstellar space. Nitrogen slabs might last longer if they were large and clean. For numbers, the required mass loss would be small per second, yet sustained. A few grams per second over weeks can shift speed by meters per second. But to survive a million years, the original piece must be big. Net result, exotic ice can explain stealthy thrust, but struggles with longevity. Sunlight is not weightless to a sheet. It pushes, gently but non-stop. Radiation pressure is the tiny force light exerts when it strikes and reflects. This matters because a very high area to mass ratio can move a body. Light pressure at Earth's distance is a few micronewtons per square meter. To get the measured push, you need around 1 square meter per kilogram. That is heavy for metal, but easy for a foamy, porous aggregate. Mechanically, sunlight hits a wide surface and transfers momentum to it. The push scales with brightness, so it fades with the square of distance. A tumbling sheet averages the force over its spin, still mostly radial. Example in real terms, a 100-kilogram clump with 100 square meters could fit. A fractal dust fluff with density near 0.01 grams per cubic centimeter works. That material would look dark yet be light enough to surf sunlight. Bottom line, a natural sun sail of fluff is plausible, without invoking artifice. Now watch the light curve, rising and falling like a heartbeat in data. The light curve is the brightness record that reveals an object's spin. It matters because spin and shape change how forces add up over time. Oumuamua's brightness swung by roughly 2.5 magnitudes. That implies a shape with a large aspect ratio, like 6:1 or more. The rotation period was near 8 hours, with signs of complex tumbling. In physics terms, it likely rolled in a non-principal axis state. Sunlight then pushed different faces as it turned, but averaged outward. A flattened, pancake shape can match the observed flicker as well. Example, a disc just tens of meters thick but long across could fit, or a cigar twice as long as a soccer field, twisting as it cooled. Both produce large brightness swings from the changing cross-section. So the picture is this: odd shape and tumble can mask a simple push. Imagine a fragile foam built from dust, like frost grown in microgravity. A dust aggregate is a loose, porous body with lots of surface area. That matters because trapped gases and weak bonds can release without bright plumes. Heat seeps in, then weakly bound molecules desorb from grained surfaces. Microjets form between pores, producing thrust that is smooth and faint. Sintering can stiffen parts, while cracks open new channels as it turns. The thrust follows sunlight, so it points mostly away from the sun. Example with a number, density near 0.01 grams per cubic centimeter gives lift. At that density, 1 kilogram can spread over a square meter of area. A few grams per second of desorption for weeks would change speed by meters. Debris would be large grains, too few and heavy to glow as a coma. Bottom line, a foamy rubble body can hide its jets, yet still get pushed. 16 months later, another traveler arrived, and it looked normal. 2I Borisov was a textbook comet with a bright coma and a tail. That contrast defines the stakes. Oumuamua might be rare, or we missed its plume by timing. Wide surveys are our fix, because early detection beats deep, late images. The Rubin Observatory will scan the sky with fast cadence. Software will flag movers nightly, then route alerts in minutes. Spectra and thermal data will follow, while the object is still inbound. Example numbers, Rubin could find tens of interstellar visitors each year. Days or weeks of warning mean we can catch jets as they switch on. We can even schedule radar or chase probes for the brightest cases. Net result, more samples will break the tie between models, and soon. Here is the calm truth. The first interstellar rock surprised us, then left questions behind. We learned that tiny forces matter when you watch precisely and long. We also learned that nature can mimic a sail without shiny panels. Maybe it was exotic ice, maybe fluffy dust, maybe both in layers. The callback is simple. Something really did travel faster than it should. If you enjoy mysteries that resolve with better data, stick around. I post deep dives like this, paced for curious minds. One gentle ask, tap subscribe so you catch the next visitor's story. Bottom line, the cosmos keeps sending puzzles, and we finally have eyes to solve them.